In tutorial 4, we explored a few of the important properties of finite impulse response filters. We learned how we could specify the filter kernel and how we could affect the roll-off and stop band characteristics using window functions. The specific application we explored was simple filters. Before we proceed, I would like to make an appeal. The driving motivation for DSP Explorer was to provide an environment which allows you to write your own code and experiment with the various algorithms. I implore you to write code and make these tutorials interactive. Nothing teaches like doing, and I humbly ask you to do. Extremely powerful DSP techniques require only a few dozen lines of code. The beauty of software is that the only cost of failure is your time. In this tutorial, we will explore the use of finite impulse response filters as they are applied to phasing techniques used in most software-defined radios. Before we look too closely, let's do a quick overview of how a phasing rig works. Since we are interested in the digital signal processing aspect of phasing rigs, our example will start at the analytic signal consisting of I and Q. Please note that the I and Q signals can be constructed in several different ways. The two most common ways appear to be the use of quadrature sampling detectors and what are called direct sampling detectors. Each approach has its own merits and its own drawbacks. Fortunately, for this discussion, both generate a simple analytic signal, and the digital signal processing which follows is generally independent of how the analytic signal is produced. So let's start by reviewing how a typical phasing rig works. This technique is a general approach and essentially the same in both analog and digital radios. As we have stated above, the phasing rig starts with a circuit which generates I and Q signals. When we first wrote our SIGGEN module, we had the foresight to provide both I and Q signals and the analytic signal S. Let's look at the waveforms as we scan our frequency from negative to positive frequencies. I have chosen to examine all three outputs of the SIGGEN module. I am displaying the analytic signal called S as the spectrum, here, and the I and Q signals as time displays. I have overlaid the I and Q signals so that it's easy to see their phase relationship. Notice that when the spectrum indicates a positive frequency, the blue trace precedes the red trace. When the frequency is negative, the red precedes the blue. Right now it's negative on the left-hand side of the spectrum. And if we wait long enough, this will come back to the middle, go through zero frequency, and then go into a positive frequency, and the order of these two signals will change. Now the blue precedes the red. A phasing rig works by introducing a phase delay of 90 degrees into the I or Q signal. Once this is done, the two signals are either exactly in phase or exactly out of phase. But how do we introduce this 90-degree delay in a signal? Well, back in tutorial 2, we noticed that if we change the phase of the reference signal, what we now call the filter kernel, we could introduce a phase change in the output of that filter. Thus, we need only introduce a wideband filter with a phase delay of 90 degrees. We have all the building blocks necessary to create this program, and I've already done it in phasing rig 2. Here we have our signal generator, and we had a wide signal reference to generate a wide kernel. Set this to be 0.5 for now. And we have our general FIR, and we can run this. We can adjust this delay in our phasing rig. Here I'll set it to 0.75, which is minus 90 degrees. When we run this, however, we find that the output of our 90 degrees phase shift filter and the I channel do not track. Why is this? Here's our I channel, which is we are trying to match with delaying Q, and we see that they don't match. So why don't they match? As it turns out, it is because the general FIR module introduces two delays to our signal path. One is the 90 degrees we had hoped for, and one is a fixed delay referred to as the group delay. We can see this if we look closely at the waveforms. These are a little jittery, but we can see that the trigger point is in the center of the screen. This is an unmoving point. Everything on this side expands this way. Everything on this side expands this way. So this is our trigger point. Now if I look down here at the output of my general FIR and try to find an equivalent place, it's somewhere in here. Everything to this side expands away. Oh, looks like it's right here. Everything to this side expands the other way. Now let's set our phase to be 0 and look again. Here we find our point that doesn't move somewhere around here. Everything to the right goes right, everything to the left goes left, so the inflection point is somewhere right about here, underneath this line, for example. And if I stop this waveform and I look at this signal with the bar, remember the unmoving point was somewhere here, I can count the number of bars back to here to see what our fixed delay is. So let's start about here. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. It's 32 or 33. As it turns out, the delay is half the length of the FIR filter. In this case, it's 32. Let's introduce this delay into the I channel, an equivalent delay into the I channel, by putting in a shift register. We'll say it's 64 long. We'll do the tap at 32. We'll run that there. Let's go ahead and run this. Run. And let's compare this output, the tap, with the general FIR. And set our phase to back to 90 degrees. And we can see that this delayed version of I, delayed 32, is now tracking the phase delay that we had hoped for. This signal and this signal are now tracking. Now let's look at our sideband selection using a simple math module and look at the sum and difference. I did that in phase rig 3. Here I added my math module. I've set this delay, set the phase, wideband, general FIR, shift register, and I'm going to look at the sum and the difference. There's the sum, there's the difference coming out of the math module. Let's run it. So let's go ahead and scan both positive and negative frequencies and look at these signals as signals. And as this scans back and forth, we're going to see the blue signal arrive and the red signal underneath. So now we're looking at the addition of these two. And when the frequency jumps back above 0, the blue signal has gone away and the red signal arrives. So let's look at one sideband only. And display things in dB. Now let's look closely at the opposite sideband rejection. In this case, the sideband we're looking at is subtract. The upper sideband is subtract. And here's the opposite sideband rejection. This is what bleeds over from the negative to the positive side, or in this case, from the positive to the negative side. This looks familiar. It has problems down here around 0, but even when it gets away from 0, it's still down only by about 30 dB. This is really quite poor by modern standards. But we've seen this before. This is really just like the roll-off of a normal filter. The shape is exactly the same. Perhaps we can use a windowing function to help reduce this. Let's try it. Do Blackman. Now we saw that Blackman changes the amplitude of the signal passing through it, and we're going to compensate for that here. We'll run this again. Now we'll notice that the opposite sideband rejection down here is even poorer at low frequencies, but once it gets its stride, it's substantially better. The opposite sideband rejection is first lobe is down here, about 80 dB below. Before we move on, I'd like to point out that this general FIR module, coupled with this wideband filter with a 90-degree phase shift, is called the Hilbert transform in the literature. There is extensive literature concerning the implementation and the properties of this extremely important function. Note, however, that it is really just another example of simple correlation. One variation on the above approach is shown in phasing rig 4. Here, the shift register delay is replaced by a second general FIR module. When this approach is used, the two modules are set to provide plus and minus 45 degrees. I call this the matched FIR approach. There are several justifications given for this approach. First, the theory is that the amount of passband ripple is reduced because the matched modules will have the same passband ripple to begin with. The literature indicates that this is not the case, and experiments with DSP Explorer have verified this. The stop band also appears to be worse with the matched module approach. It is possible to compensate for this by extending the length of the FIR kernels. For example, the literature indicates that a Hilbert transform length of about 30 performs the same as the matched FIR structure with a length of 100. The second supposed advantage is that the matched modules allow one to set the passband in the two modules, thereby eliminating the need for subsequent bandpass filtering. This helps reduce the overall processing required for the matched approach by eliminating an entire passband FIR, but the total processing load remains greater. For example, the matched FIR filters of length 100 compared to a Hilbert transform of 30 plus a passband of 100. The total on the matched approach would be 200. The total on the Hilbert plus passband would be only 130. The third advantage probably holds up. Since the matched modules are the same length, there is no confusion when determining how long the delay must be. The kernels can be any length, even or odd, and there is no need to worry about matching the gains of the two channels. Indeed, it is easier to code for the two modules, and there is much to be said for that. If one can afford the extra processing required, the matched FIR approach probably makes sense. In this tutorial, we've explored the high-level implementation of phasing rigs using DSP techniques. We've found that designing phase delays is really just an exercise in low-pass filter design. The techniques we use to improve our filter design are equally applicable to phase delay modules. In the next tutorial, we will extend the principles of FIR filters and correlation to analytic signals and springboard this into the discrete Fourier transform.